Hey guys, we're now starting our new unit on chemical bonding and nomenclature. So some of you mentioned that you'd rather me do the videos than I send you to other places, but I'll be honest, people like Tyler DeWitt and Bozeman Science, Brightstorm, Khan Academy, all those places are really great resources to use and definitely do a better job than I do. I mean, they get paid to do that kind of stuff and do a really nice job with them. But for right now, I'll try to get you guys the basics and then I'll defer to you. I'll defer you to them for a little bit more information if you need me. So to make a long story short, as you'll notice on the screen, you'll see 4 things. We're going to be specifically studying 2 of those things, 2 of which I'm sure you already are aware of, which are the ionic and the covalent bonding. So I'm going to switch to the other the other camera, and we're going to go into a little bit more detail as to what's going on with each of them. Okay, so as you can see, for chemical bonding, these are the main types that we were talking about. You've got ionic, you've got covalent, and then you have metallic. I'm going to slide over to metallic first and discuss just a little bit about metallic, and that's basically about all we're going to talk about for the rest of the unit. Okay, so metallic bonds, they're known because they have a sea of electrons that are occurring within a metal. So a lot of times people like to say it's a metal plus a metal type of a bond, when really it's not really a metal and a metal, it's the bond that's within one metal. So like if you were talking about copper metal, why do the copper bonds occur in a piece of copper? Because all of the atoms have all those little valence electrons, as you learned, the electrons in their outermost shell, and those little electrons actually freely move about, which is one of the reasons why metal is so conductive. It has all these little electrons that are easy to flow. So the sea of electrons within one specific metal. Okay. Other than that, for right now, we're going to skip anything else with metallic bonds, just so that you know there is a bond between a metal versus a metal, and again, really within itself. But we're not going to study those for right now. We're instead going to start focusing more on just the ionic and the covalent. So now when we talk about ionic bonds, you'll notice that it says an ionic bond happens between a metal and a nonmetal. All right, and that is specifically an ionic bond. Ionic bonds occur between a metal and a nonmetal, and they give and take electrons. All right, and I'll explain all of this stuff a little later, but I just want you guys to be aware of the main points of each one of them. Whereas a covalent bond happens between a nonmetal and a nonmetal, and they share electrons. Okay, so now we have to do a little bit of review. And that little bit of review is going to be quick since we just finished our periodic table unit. All right, so I'm going to slide this out of the way really quick. Okay, here's my handy dandy periodic table. And as we hopefully now remember or know, let's put it that way, our metals are on one side of the periodic table, our nonmetals are on the other. So remember, this silly little line here separates our metals from our nonmetals. All right, so that staircase, that's imaginary. Everything to the left of it is a metal. Everything to the right is a nonmetal. The only difference or the only exception to that rule is what? Correct, hydrogen. Hydrogen is the only element on the periodic table that is on the wrong side. Hydrogen should be with all the other yellow guys over here, which is a nonmetal. Okay, but for some reason, hydrogen is listed over here, and it's really only because of its one little valence electron. But for all intents and purposes, remember that hydrogen is a nonmetal. All right. Now, for example, if I put some marker here and I put a marker there, okay, that's Na and Cl. That is a metal coming together with a nonmetal. If that's the case, they're on opposite sides of this zigzag. Okay, like people try to say that it's ironic that things get together. Okay, well, I say ionic is ironic. They shouldn't get together. They're on opposite sides of the periodic table. They're too far away from each other. So we call that an ionic bond, a metal and a nonmetal. However, if you put 2 nonmetals together, like N and Cl, you now have what's called a covalent bond. Covalent because they are both on the same side of the zigzag, sharing the same space, like coworkers. Coworkers cooperate together to share the same space. Okay, or if you can't remember it, C and O, notice they're on the same side of the zigzag. Covalent, share together on the same side of the zigzag. Of course, remember, the only exception to that rule is hydrogen. So hydrogen shares with any of these over here. That is a covalent bond. All right, so I'm going to trick you. What happens if I said this? All of you would like to say that that's a covalent bond. And technically it is because, of course, the noble gases are indeed nonmetals. But what's the trick that I'm trying to get you? You're right if you said that these guys aren't going to bond. Our noble gases will not bond. And because of that, we call them inert, remember? So because they are inert and they do not bond with anyone, we ignore them for all intensive purposes when we're talking about bonding in this unit. Okay, so if you ever see something with a noble gas, ignore it. It is not going to bond. All right, so for example, keep that line there. Here we go. Okay, so if you have two there, you know that that's going to be a metal and a nonmetal. You've got an ionic bond. Ionic. 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 Are you getting the point? It doesn't matter where they are on the left side, as long as one's on the left side, one's on the right side, it's ionic. Now, talk about covalent. Again, same thing's going to happen. No matter where you put them, they are covalent. All right? Here's the one trick question that's going to now get some of you angry. What if I did that? Okay, before you guys learned that these are metalloids. It's kind of hard to see, but there's a little bit of color differentiation between these guys. Okay, so these are metalloids, metals and nonmetal combinations, right? What you need to know is that for right now, this is our determiner. This is our separator. So if they are on this side, they're a nonmetal. If they're on the left side, they are a metal. So Ge, Sb, and Po are metals. B, Si, As, and Te are nonmetals. So if it's like this, that is an ionic bond. If it's like that, that is a covalent bond. I know it's irritating, just go with it. And remember, if I do this, technically we're not studying that metallic bond, and in reality, a metallic bond is literally just that with that. Or if I want to be more specific, since that's made of zinc, zinc. All right, so our two examples that we have, I have Na and I have F. There's Na and F. That is definitely an ionic bond, which is why I said it is ionic. So now let's get into a little bit deeper about the difference between the ionic and the covalent when it comes to the actual bonding that they're going to do. Okay? Okay, so in an ionic bond, when you have a metal and a nonmetal coming together, this is what you're going to see. Here's sodium. Now remember, sodium has 11 electrons. That's why we have 2 in the first, 8 in the next, which is 10, plus 1 more is 11. There's my 11 electrons. Fluorine is number 9 on the periodic table, and it has 2 plus 2, 4, 6, 7, which is a total of 9 electrons. All right, now, for those of you that remember, sodium being in the first column, because sodium is in the first column, it has 1 valence electron. So if you look here, there's my 1 valence electron. Fluorine has 7 valence electrons. Yes, it does, because if you look at the top of the column, it's group 17, or hide the 1, and there are 7 valence electrons. Remember, the goal is to get 8. That outermost electron shell needs to be full with 8, octet rule. So what happens is sodium is extremely happy to get rid of this electron. Okay, it has a really low electronegativity and ionization energy. Remember, all it wants to do is lose an electron. Fluorine has a high electronegativity and ionization energy. It wants to gain an electron and not lose any. So metals will always give to a nonmetal. Okay, so my metals are my givers. They give. give. And my nonmetal will always take. Take, take, take. It could take 1, it could take 2, it could take however many it needs to become stable. All right, so in this case, sodium is going to give to fluorine, and in the end, this is what happens. Ready? Now your sodium loses this outer shell. So that outer shell goes away. That extra electron is gone. The extra electron, is given to fluorine. And now if you'll notice, I have 1, 2, 3, 4, 5, 6, 7, 8 in my outer shell. 1, 2, 3, 4, 5, 6, 7, 8 in my outer shell. They both have 8. They are both happy, and they both, believe it or not, look like neon, which is a noble gas. They are extremely happy. Every element on the periodic table, that's their goal, is to look like a noble gas. Okay, we talked about that before leaving to go home. So I could do this with another set of elements, and I'm going to do that right now really quickly. But before I move on, I want to show you one more thing. If I were to name this, you all can do this. The first element in an ionic bond is always named with just saying the element. So Na is sodium. The second element is fluorine. So you would write fluorine. I'm just going to write fluorine for right now. And yes, believe it or not, the U comes before the O. It's not flour, it's fluorine. Except there's one little thing that you need to change when we come to naming. Instead of it being sodium fluorine, and you guys know it sounds weird, instead it should be ide. So when it's all said and done, your naming for ionic bonds is sodium fluoride. Sodium fluoride. Let's try another example. Okay, so here's another example. Magnesium and chlorine. So if I look on the periodic table yet again, they are indeed a metal and a nonmetal. Okay, instead of writing the Bohr models for these, now we're just going to make it a little bit easier. We're just going to go to the Lewis dot structures. And if you'll recall, the Lewis dot structures just show the electrons in the outermost shell. So if that's the case, here's magnesium. It's in my second column, which means it only has 2 valence electrons. So I'm going to draw my 2 valence electrons for magnesium. 1, 2. All right, and then chlorine. It is in group 17, just like fluorine was. So if you look, cover the 1, and that's 7 valence electrons. So I'm going to do my 7 valence electrons. And you really want to think of there being this imaginary box around the elements. This imaginary box, and you want to put 1 electron around each side first, and then go back and double them up. Just like when you were doing the electron orbital diagrams, right? It doesn't matter if you put 1 here and then 2 here, or 1 on the top, 1 on the bottom. Generally speaking, because they're electrons, they want to be as far away from each other as possible. So that's why we usually do 1, 2. Depending on who you ask, they'll say 1, 2. It doesn't matter. The important thing is don't put both of them at the top. All right, so now notice something really, really important. Magnesium has 2 dots, chlorine has 7. My magic number is 8. My magic number is 8. All right, so if chlorine has 7 dots, you all know that it needs only 1 more. So in an ionic bond, magnesium is going to give its electrons to chlorine. The problem is it has 2 electrons, but chlorine only needs 1 more. So if chlorine gains this 1 electron, now he has 8. 1, 2, 3, 4, 5, 6, 7, 8. He's done. But notice magnesium is irritated because magnesium still has 1 electron and that it wants to give away. It does not want that electron. It wants to have that noble gas shell configuration of no electrons in that outermost shell. So what it's going to do, I'm going to erase my 8, is it still has to give that electron away. Well, guess what? It's a metal combining with another nonmetal. So could I draw another chlorine or another magnesium? Let's do this. If I draw another chlorine, magnesium, we said, gives away its electrons to chlorine. So magnesium gives that electron away to chlorine. And now notice each chlorine atom, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, has 8. They are content, they are perfect, and you're done. Okay? Now, because magnesium gave 2 electrons away, magnesium ends up with a +2 charge. That's where those charges come from, or oxidation state. And each chlorine, now you have to look at each one individually, not as a total. So if I cover this one up, how many electrons did that chlorine take? It took 1. So that's a -1 on that chlorine, and that's a -1 on that chlorine. So each chlorine is a -1, but you have 2 of them. So when you write the formula, it looks just the way it says. It's magnesium, and then 2 chlorines, but we write it MgCl2 to signify that you have 1 magnesium and 2 chlorines. And just like before, how do we name it? You name the first element the way it is. So the first element is magnesium. And then the second element is chlorine. Except what did we say that you had to do to the end? You are correct. Change it to "ide." It even sounds silly. Magnesium chlorine? No, magnesium chloride. All right, so notice the first element stays the name that the element is. The second element changes its ending to IDE. That is basically your ionic bonding examples. I can give you one more and then I'm done. So I'm going to write it and then I'm going to give you guys a couple seconds to see if you can figure it out. Okay, here it is. Al and Se. Okay, if you look on the periodic table, there's Al, aluminum, metal. There's Se, non-metal. So now we have to figure out what's happening with each one of them. Aluminum is in group 13, which means cover the 1, you have 3 dots. So I'm going to put 3 dots around aluminum. 1, 2, 3. Selenium is in group 16. So how many dots? 6. You are correct. So I'm going to put 6 dots around him. 1, 2, 3, 4, 5, 6. Really, I should have gone 1, 2, 3, 4, 5, 6. Sorry, I've been doing them so many times I already know what to do. All right, so you have your metal, you have your non-metal. Metals always give, non-metals always take. Take, take, take. So, aluminum wants to get rid of all 3 of his electrons. Selenium needs how many more if it wants to have 8? 2 is correct. So, aluminum is going to give 1 there, and it's going to give 1 here. So now I have 1, 2, 3, 4, 5, 6, 7, 8. Selenium is perfect. Okay, here's where you're going to get angry. Here we go. Aluminum has 1 extra electron. It doesn't want it. It needs to get rid of it. And who did we say it has to get rid of it to? Correct. Selenium. So let's draw another selenium. 1, 2, 3, 4, 5, 6. And get rid of that electron. So aluminum gets rid of that 1 electron. Uh-oh. Now what's wrong? Aluminum's perfect. It has no more electrons. He's done. But selenium still needs 1 more electron. Well, what does selenium get its electrons from? You're right, aluminum. So we draw another aluminum. 1, 2, 3. Aluminum has to get rid of its electrons to selenium. This one's already full, so it can't go to that one. This selenium still has 1 spot available. So we're going to give 1 of its dots to selenium. But now aluminum is stuck with 2 electrons still. Guess what? You nailed it. You have to draw another selenium. And if we do it, you'll notice it all works out in the end. Selenium has 6, wants 2 more. So aluminum is going to give 1 there, and 1 there, And now selenium has 1, 2, 3, 4, 5, 6, 7, 8. Check. 1, 2, 3, 4, 5, 6, 7, 8. Check. 0, 0. So, in the end, what's the charge on each aluminum? Each aluminum is getting rid of 3 electrons, so it's a plus 3. Each selenium is taking 2 electrons, so each selenium has a minus 2 charge. So if we write the formula for this, it would look something like aluminum and selenium. And now we write the numbers. How many aluminums? There's 2. And how many seleniums? 1, 2, 3. So our formula is Al2Se3. And if we name it aluminum, okay, this one's going to be ugly, selenium. But instead of aluminum selenium, it's aluminum selenide. Selenide. Aluminum selenide. All right? Aluminum selenide. All right. So just do your best at naming. It's going to sound funny, like phosphorus is not phosphoride, it's phosphide. Sulfur is sulfide. Silicon is silicide. That one's pretty ugly. Carbon is carbide. Hydrogen is hydride. The rest of them I think are pretty obvious after that. All right, so now I'm going to show you one last thing and then I'm done. There is obviously a shortcut to everything we do. You ready to see the shortcut? Okay, you guys told me that each aluminum is a plus 3, right? Because they each gave away 3 electrons. Look at the top of my periodic table. Oh, aluminum's plus 3. Look at selenium. Each one took on 2 electrons, so it's a minus 2 charge. Well, if I look at my periodic table, selenium is a minus 2. Huh. So you mean to tell me that all I had to do was really write a plus 3 here and a minus 2 here and say, okay, wait, if they don't equal 0, there's the 2, there's the 3. Believe it or not, that is the shortcut, but I'm still going to make you do this, but that is the shortcut to writing a formula. If your charges, a plus 3 and a minus 2, don't cancel out. A plus 3 and a minus 3 cancels out. A plus 3 and a minus 2 does not. They do not cancel out. You crisscross the numbers. So you drop the 2 there, and you drop the 3 there. Some of you will remember doing this. Okay, so I'm going to do 2 more, and then I'm done. Here's your first example. I have magnesium again with a plus 2 charge, and oxygen. Okay, I'll let you finish that one. And I'm going to give you sodium, and let's do arsenic. All right, so magnesium is a plus 2, and oxygen minus 2. So does a plus 2 and a minus 2 equal 0? It does indeed. So we're done. So our formula in the end is just MgO. Now look at Na and S. Na is a plus 1. As is a minus 3. So As is a minus 3. Does a plus 1 and a minus 3 equal 0? The answer is no, they don't cancel out. That would have to be a plus 3 or that would have to be a minus 1. So if they don't cancel out, they're going to crisscross those numbers. So the 3 goes there and the 1. Notice it's just the numbers and not the charges. So Na3AS1, and when it's all said and done, that 1 is understood just like in math. So it would be Na3AS. Now, well, how would you name them? First one would be magnesium oxide. The second one, that's arsenic. So that's sodium arsenide. And that's basically ionic bonding in a nutshell.